Hello, students. Welcome to the class. This session is fourth in series of the chapter Gravitation. By this time, you already know that, right? This Gravitation is chapter 9 in CBSE and chapter 10 in Karnataka State Syllabus. Let's look at the index again. So this chapter contains gravitation, free fall, mass, and weight. We covered, gravitation, free fall, mass, and weight till now, right? So continuing this, we have a thrust and pressure and Archimedes principle left out. In this session, let's focus on thrust and pressure. To start with, right? Let's try to, ask ourselves a couple of questions, which we have already seen it or felt it or experienced it, right? Mm, Observe this, okay? Uh, have you ever wondered why a camel can run in a desert so easily, whereas we can't run so easily, right? Okay, why? And look at this, the army tank weighing more than 1,000 tons. You know, why this always rests upon a continuous chain? Look at it. It's it's a chain, right? Why it is always, why it rests on a continuous chain? Okay, look at the trucks here, right? Why a truck or a motor bus has wider tires? Look at our cars, right? Uh, not wider. Whereas trucks have a wider, tires. Why? Okay. Okay, why cutting tools have sharp edges? Look at this. These are the knives and other cutting tools, right? Why they have a sharp edges here? Why they have a sharp edges here? Right? Why they have sharp edges? Have you thought about it? Okay. Now, let's get little bit deep. Dig deeper, right? So the way we can understand all these, phenomena or things, right? We can go in two directions. One way is this way. One is this way. Okay, let's go with, see, we learned already force, right? All of previous sessions of force, are focused on force. Now, from that angle, if you say that, so we can, all these wonders or the phenomena can be understood uh, uh, either considering or talking about net force, one hand. Other one is a force per unit area. Net is always sum of all, right? Remember, it's sum total of. Okay, we can consider a net force at a given area maybe. Okay, and force per unit area, right? So if it can focus, dig deeper into these concepts, right, we'll be able to understand those phenomena which the questions we asked ourselves, right? Other way to understand the same phenomena is, using the scientific terms. These are the physics terms again, technical words, right? What are those technical words? Thrust and pressure. Remember, these are related. The left branch and right branch are related.
Okay, and now it's time for us to understand the meaning of the technical words thrust and pressure. Okay, let's understand this by considering two scenarios or situations. Okay, let's go with first situation now. Assume you wish to fix a poster on a bulletin board. Okay, as shown in the figure. You know, to do this task, what you need to do? Okay, you will have to press drawing pins with your thumb. Where will be the drawing pins? Maybe somewhere here. Uh, right, so maybe here, 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 here. Okay, you apply a force on the surface area of the head of the pin. Okay, like this. You see this region is zoomed. Okay, see this. This is a pin here, and you're using your thumb here, and you're pressing it. Okay, see, you're using your thumb to press it. Okay, press the head of the pin, right? So this force, you pressed it, remember, this force is directed perpendicular to the surface area of the board. How do you understand this? So now this is a wall, right? This is a wall, and you're pressing it this way. Okay, it's perpendicular, remember. Okay, the force is directed perpendicular to the surface area of the board. This force, you are, whatever you pressed it now, right? This force acts on smaller area. It means at the tip of the pin. Look at this This pin is so small and its head is so small. Whatever you press, whatever the force you're using is acting on a very small area, that is on the at the tip of the pin. Okay, the two things remember here. What happened? What's we're considering? We are putting a pressure and we are putting a pressure constrained to a small area. Two things. Okay. Now, so what is that we learned now? See, now we learned the concept of net force. Net force means sum total of all force, all force together, right? So look at entire force is now concentrated on the small area. That's net force, entire phase, okay? Force. In a particular direction, right? On the small area. So we call this, of course, this force is a thrust, we call it as, okay? Now, consider the situation 2 now, right? Okay, you stand on a loose, just imagine yourself standing on a loose sand. Your feet will go deep into the sand, correct? Maybe imagine yourself in the beach, somewhere here, or maybe in the mud. Okay, you stand on a loose sand, okay, and your feet will go deep into the sand. Why? Okay, naturally, because you apply some pressure, weight is a reason, right? Now, lie down on the sand, okay, don't lie down on the sand, like maybe this way, right? Right, you will find that your body will not go deep into the sand. It will not go deep into the sand, okay? Okay, in both the cases, the force exerted on the sand, both the cases, the force exerted on the sand, I mean, they are not equivalent, the sands, remember, but, I'm just trying to give you a best possible analogy, which I got it now, from, in both the cases, the force exerted on the sand, okay, is the weight of your body. Remember, here also the force you're exerting is your weight of your body. Here also your force you're exerting is your weight, right? Okay. Okay. So now what is that we learned from here? What is the concept we learned now? See the force per unit area. Look at it. Your force in this case, what is the force? Your weight area, right? The area is spread across this wider area, whereas your weight, right, that force is concentrated in the small area, right? But in both the scenarios, the force is your weight and it is equal, okay? So the force per unit area acting on the object. So that's what we learned. So here is we learned about net force, and you had compared net force and the force divided across the area, okay, spread across the area, or force per unit area as a concept. Okay, let's elaborate the same concept again. That is force being spread across an area and force being concentrated in a small area, right? So now we are relating force to the area. Okay, before this we were talking about force. That's all. Okay, force and acceleration. We are never bothered about area, right? Now we are talking about connecting slowly the force with area on which it is acting upon, right? So now let's start. When you stand on the loose sand like this, okay, like this, okay, when you stand on loose sand, the weight of your body is acting on a small area equal to the area of your feet, right? See, the area of your feet is this much, right? Entire weight, okay, is acting upon the small area, that is equal to area of the weight. When you lie down like this, right, okay, the same force acts on the area which is equal to the contact area of your whole body. Look at the contact area of your body is this long. Here the contact area of your body is just small, right? The feet, right? Here contact area is quite more. So the same force acts on the area equal to the contact area of your whole body, which is larger than the area of your feet. Of course, it is pretty much visible, right? Area is larger, the contact area, okay? Now, thus, the effects of the force of the same magnitude on different areas are different. Remember, what is the force acting upon it? Which is equal to weight of this guy. What is the area of the force acting upon here? This is equal to weight of this guy. Assume they are both same guys and they have the same weight. In both the cases, the force acting on is same, which is equal to the weight of the guy, the boy, right? When the forces are same, the magnitude of the force is same, but then the effect is not same. Okay, the effect is not same. In the left side, your hands, your legs are inside the mud, but in the right side, no, you're just on the surface. Okay. In the above cases, thrust is the same. It means thrust is equal to what? Weight. That is equal to what? Force, right? The thrust is the same, but effects are different. You know the difference in effects, right? It is visible in the images. Therefore, the effect of thrust depends on the area on which it acts. What do you mean by that? It means though the thrust is same, but the effect of the thrust is different, right? But that effect of the thrust depends on area on which it acts, right? More the area, different effect. Lesser the area, different effect. Okay. The effect of thrust on sand is larger, okay, while standing on while standing than while lying. Okay, what is the mean by that? Wait a minute, so I'll clear it up. Okay, what is the meaning of it? The effect of thrust on the sand is larger while standing. So effect of thrust is larger while standing than while lying. Simple, right? Right. The effect of thrust when acted upon a small area is is more. That's what he's trying to say. Okay. So now the thrust on unit area is called pressure. Remember, now we are slowly connecting it thrust and the pressure. Okay. The thrust per unit area or thrust on unit area is called pressure, and let's give it formula shape, right? Mathematically, let's put it. So now what is that? Thrust per unit area means pressure is equal to thrust by area. Clear, right? If pressure is equal to what? Pressure is thrust, but per unit area. Good. Now let's come to some more concepts or summarize this discussions. Thrust unit, of course, what is thrust? See, what is the unit of force? Newtons. What is the unit of weight? Newtons. What is the unit of thrust? Newtons. Remember. Okay. Now, what is this? Pressure is kind of a thrust, right? But measuring per unit area, right? So thrust unit Newton, when it is divided by area, of course, whose area is, what is the unit of area? Meter square, right? The square meters. Okay. Then what is the unit of thrust? What is the unit of pressure? It is Newton per meter square. This is the one. Newton per meter square. Now, honoring scientist, the Pascal, right? The scientist Blaise Pascal. We use the unit for pressure as Pascal as well. Actually, SI unit is Newton per meter square, but we honor in the honor of great scientist Pascal, we use Pascal, PA, as a unit of pressure. Okay, good. Now, let's consider some numerical examples to understand the effects of thrust acting on a different areas. See, better always do, go and solve some look into the numerical examples or solve some numerical problems, to understand some of the physical, the terminologies and their effects, okay, how they work, okay, how they behave, right? So now let's consider one such. Okay, example 9.6, of course it's taken from the book. Okay, let's solve it in our own way, right? A block of wood is kept on a laptop. Imagine a tabletop. Just imagine a tabletop. You're placing a block of a wood. Maybe it's think like a cubicle shape or some some shape. Okay, the mass of wooden block is 5 kg. The mass of wooden block is 5 kg. Okay, just think of this. I'm just giving you visualization. So this is a wooden block, okay, and its weight is how much? 5 kgs. Okay, and its dimensions are 40 centimeter, 20 centimeter, and 10 centimeter. Look at this. This is 20 centimeter this way, 10 centimeter this way, and height is 40 centimeter this way. Okay, find the pressure exerted. Now I need to calculate the pressure exerted by the wooden block. Pressure. Okay, I need pressure block. Okay, block on the tabletop, because we placed it on tabletop. How much pressure is exerted by this wooden block on the table? That's what I need to understand. We need to understand, right? Now there are two possible, a couple of ways you can place it. One is I make it standing. I can make it sleeping. When it is make it standing, maybe I have height, vertically upwards. Okay. When it make it lying, maybe I have 40 centimeter, side, 40 and 20 centimeter side, touching the tabletop. the two scenarios, right? Now we need to understand, is it pressure exerted by these two scenarios, okay, is it same or different? Okay, let's solve it, okay, mathematically. Now, as we know that, right, we, as always, we start with data that's given, okay, and we use concepts, and then we use formulas, related formulas, right, and then we go for subsection of subpart of a problem, like for example, will a block lies on sides with 20 centimeter and 10 centimeter, this first case, right, this case, okay, and we also we need to solve what is the thrust, what is the pressure exerted by this block when it is lying with sides 40 centimeter and 20 centimeter. See, the 40 centimeter is touching and 20 centimeter is touching the product top. Let's go solving it. Okay, what is given? The mass of the wooden block is given. Remember, what is the unit of mass? Kg. Okay, 5 kgs is given. What are the dimensions? What is the dimensions? You know that, right? So, what are the dimensions here? 40 centimeter, 20 centimeter, 10 centimeter. Volume is a multiplication of that. But then dimensions are given, three sides, right? 40, 20, and 10. 10 all of the they are measured in 10 centimeters. Observe this. Okay. Okay. Centimeter is not an SI unit, so we always use meter. Okay, as a SI unit, right? So let's convert these units into meters. Okay, I'll tell you why we use meters later. Okay, 1 meter, we know that is equal to 10 decimeter, right? That is equal to 100 centimeter, right? That is equal to 1000 millimeter, correct? Now, what is our interest is centimeter, because it's given centimeter. Okay, so now 1 meter is equal to, I'll take that part. 1 meter is equal to this portion, I'll take it. Okay, 1 meter is equal to 100 centimeter. Then what is 1 centimeter now? So I can replace 2 zeros left side. Okay, how much is that? 1 centimeter is equal to 0.01 meter. Okay, then let me put them here, convert them, 40 centimeter and 20 centimeter and centimeter, we will convert them into meters now. Let's do that. How is that? Now see, 1 centimeter equal to 0.01 meter, right? 40 centimeters equal to how much? 40 into 0.01, 0.4 meters. Right. Similarly, 20 centimeter is equal to 20 into 0.01, that is equal to 0.2 meters. And 10 centimeter is equal to 10 into 0.01 meter, that is equal to 0.1 meters. Then bring them here, because we need a units in meter, right? Right. Let's remove them. Okay. Okay. Put them here. Okay, so now what is the dimensions? Now 0.4 meter into 0.2 meter into 0.1 meters. Good. Now what is one more required? Okay, when we talk about the thrust is kind of a weight, kind of a force, right? So we always talk about M into G, right? What is M? It's given here, 5 kg. What is G? G is acceleration due to gravity. I need it's constant. Okay, so we have to remember this, 9.8 meter per second square. So you have to bite this, it will help you in many places, even in competitive exams and entrance exams, everywhere it else. Okay, what is acceleration due to gravity? G is equal to 9.8 meter per second square. What is the unit here? Remember, unit is meter per second square. See, what is the unit here? Meter. So we need to have a same units everywhere when you do simple calculations, mathematical calculations. That's what we did, conversions, right? Okay. Now, what is the concept? The weight of the wooden block applies thrust on the tabletop, correct? What is that? The weight of it. See, this wooden block has a weight, and this weight applies thrust on the laptop, right? Thrust is kind of a force. Remember, okay? And what is the formula? Thrust is equal to a force. And what is the formula? Force is equal to mass into gravity. Okay, mg. F is equal to mg. F is equal to ma. Now it's F is equal to mg. Now thrust is equal to mg. So now what is that? Substitute them, right? What is this substitute? So now 5 kg here and 9.8 units here, right? So how much is that? How much? 5 into 9.8. How much? 49 newtons. Remember, this is a thrust exerted by the wooden top on the tabletop. Okay, on the thrust exerted by the wooden block on the tabletop. Clear, right? Now let's go. Remember, this thrust or is very similar to weight, right? It will not change. Because why it will not change? Mass of your wooden block is constant. Gravity, acceleration due to gravity, which is of course the gravity with respect to the earth of the earth, right? It is remain constant. So the thrust will not change whatever the way you place this. Okay, either vertically or horizontally, doesn't change. So we calculated thrust which can be used in both the scenarios. Okay. Let's continue. Now, see, as I mentioned in the just in a previous slide, right? What is pressure? Pressure is thrust per unit area, right? It means I need this thrust is being distributed, right? Whatever the the thrust, right? This block is exerting, right? It is distributed across this area, right? This area, and what is this area? 20 into 10 centimeter, right? So a length into breadth. So now what is this area? This area, okay, which is touching the tabletop. Okay, it is coming in contact with tabletop, right? What is the area? Is equal to length into breadth, that is equal to 0.2 meter, which we did it here. This is it here, okay, and we did it here. Okay, 0.2 meter into 0.1 meter. Of course, how much is that? 0.02 meter square. Remember, let's always prefer meter as a unit, okay, unless otherwise it's required in the case. Right. So what is the area of this side? Area of this bottom side? 0.02 meter square. Let's go ahead. Okay. Now let's calculate the pressure exerted by this wooden block when it's placed vertically like this way, right? So now what is that? What pressure is equal to thrust per unit area, right? What is thrust? Thrust we calculated here, 49 newtons. What is the area we calculated here? 0.02 meter square. Now what is the value? I can say 49,000 into 0.02. See, 49 into 100 upper side. Okay, divided by 2. Right? Basically, I am multiplying in both numerator and denominator with 100. Right. So this is the way. Then what is the answer? What is the answer? 4,900 by 2, that is equal to 2,450 Newton per meter square. Why Newton per meter? This is the unit of thrust is Newton, unit of area is meter square, and I say Newton per meter square, 2,450. Okay, good. We answered this block. Okay. The first sub question: what is the pressure exerted with these dimensions touching the ground? That is in the tabletop. Okay. Now you know that, right? I already told you this thrust remains same because it is very similar to the weight of the object. Okay. It exerts same thrust whatever the way you place it. Okay. Thrust remains same. Okay, which is 49 newtons. Now let's calculate area because we need to calculate the pressure, right? So it's similar to this. Okay, what is the area? Now the sides are placed this way, 40 centimeter and 20 centimeter are touching. Okay, so what is the area? Length into breadth. So 0.04 meter and 0.2 centimeter. Look at this way. So 0.4 centimeter, sorry, 0.4 meter and 0.2 meters. And what is that value? 0.08 meter square. Okay, next go to the next one. Then let's calculate, as usual, let's calculate the pressure. Okay, what is the pressure here? The pressure is called Newton thrust per unit area, right? So what is thrust? We already calculated 39 units. Okay, what is the area? Okay, sorry, 49 newtons. What is the area? Okay, 0.08 meter square, and that is equal to how much? 4,900 divided by 8, that is equal to 612.5 Newton per meter square. Okay, now it is square. So now what is that? We just summarize it. Okay, remember in both the cases I place this way, I place this way. In both the cases, we have different areas, different sides, different areas of sides of different area touching the ground. So, but in both the cases, thrust remains same. Okay, but the pressure exerted by this way scenario and this scenario is different. Look at it. This is 2450 and this is 612. Which is bigger? This is bigger. What is the observation here? We have a bigger area here. Sorry, we have a smaller area touching the ground, tabletop. You have a smaller area touching the tabletop. So, you are the smaller the area touching the top, you have a bigger pressure. You have the bigger area touching the tabletop, you have a smaller pressure. That's what we need to take. Okay, clear, right? Answer, the final answer is simple. This is the one. This is the one. Of course, this is bigger. Okay, summary is also I'm mentioning here. I think I already told it. Same force, look at it. Both the ways, same force, 49 units, right? Same force, but acting on different areas. See, the same force acting on bigger area here. The same force acting on a smaller area here, right? Okay, same force acting on different area. So now it's not the same pressure anymore. It's a different pressure. Okay. So now what is that? Smaller the area. Of course, if the thrust or a force is acting on a smaller area, we have a high pressure. Imagine a nail. Okay, imagine knives, sharp edges. Imagine, see the areas at the sharp edges is very small. Imagine the same force acting on a small area. Pressure is too high, right? Like that. Similarly, think of a buildings where the area is bigger and the force is spread across, and we have a low pressure from the buildings. Okay, this is perfect. I think we know it, right? So I'll just clear it up, right? So now we know the very much scenario, right? Can we cut this wooden block using this side? Not so sharper or sharp. We can't cut it simply. Why? However, we can use this side, very sharp side of the cutter. Okay, and it will cut the wooden brick. Why? Because whatever the force, whatever the force or thrust you are putting is same in both the cases, but when this is below, we have a pressure more because force is acting on a very small area, resulting in a bigger pressure, and it will cut it. Okay, whereas if you reverse it, make it up and down, right? The same, but you may be putting the same force, but it is distributed across a wider area, creating a lesser pressure, and it may not be enough to cut the brick. Okay. Till now, we learned how the pressure with respect to the solids, right? Now, let's see how pressure influences fluids, or how fluids, do exert pressure. Okay, right? Pressure and solids we learned, and these are solids, right? We just now calculated what is the pressure exerted by the wooden block on a tabletop, right? So it depends on the area pressure, how much area is here, right? So now let's focus on fluids. Of course, fluids means it may be liquids, it may be gases. Okay, so now this is an example of water. Look at this is a jar, and what jar contains the water. Okay, so solids exert pressure due to weight. You know that, right? What is solids exert pressure due to weight? Pressure is equal to what? What pressure is equal to what? Thrust per area, right? And what is thrust? Thrust is equal to W weight. What is thrust? Thrust is equal to M into G, right? Mg by area. Okay. Otherwise, okay, solids exert pressure, which is function of mass, gravity, and area. Okay. Let's see what is the scenario with respect to the fluids, maybe water or air, like that. Similarly, fluids also have a weight, correct? Fluids also have a weight, right? So what is, okay, then they also exert pressure because they have a weight, and they exert pressure on a container's base and walls. Look at it, this exert pressure on the container base, as well as they exert pressure on the container's walls. Okay, so pressure exerted in any confined mass of a fluid is transmitted undiminished in all directions. It means all directions it transmits undiminished. It's not like, you know, the bottom side more or upper side less. Pressure exerted in any confined mass of a fluid is transmitted undiminished in all directions. Okay, all directions, up, down, right, bottom, all those stuff, right? Okay, now let's understand buoyancy. Okay, it's an important concept. Have you ever had a swim in a pool and felt lighter? Remember, you might be, you know, you might experience this. You know, when you are in a swimming pool or a well, you know, you're feeling light, you're feeling like you're floating on the water, right? Felt lighter. Okay, like this. Okay, have you ever drawn water from a well? Okay, you know, you remember your childhood, right? So when like uh, okay, olden days, we ever drawn water from a well and felt that the bucket of water is heavier when it is out of the well. As long as the bucket is inside the water, it's easy to take you up. The moment the water, you know, the bucket come out of the water, oh, it felt suddenly heavier. Have you felt that? Okay, so now have you also wondered why ship made of iron and steel does not sink? Look at this. This is a huge ship, and it's all made up of iron and steel and whatnot, that heavy, you know, materials. Okay, with high density, right? So this will not sink. See, so much weight of, you know, material of high, you know, weight is there, right? It's not sink. Whereas the same, you know, steel, same amount of iron and steel in the form of a sheet, right? Look at it in the form of sheet, will sink. See, this is not sinking and this is sinking, but this is in the form of a sheet, whereas this is in the form of a boat. Okay, but the amount of, you know, the iron, amount of steel is same here, but one sinks, one doesn't sink. Do you know why? Have you wondered why? These questions, you know, can be answered by taking buoyancy into consideration. Now it's time for us to understand what is buoyancy. It means why this floats, why it sinks. Why this guy, as long as you're in the water, it feels light. Why, you know, why this bucket was feeling light inside when it was in the water, and suddenly it feels heavier the moment it came out of the water, right? So buoyancy. Okay, let us understand the meaning of buoyancy by doing an activity, some activity. Okay, okay, take an empty plastic bottle, you know, some water bottle, mineral bottle, like this. Close the mouth. Okay, okay, close the mouth means inside this, you know, only air, no water. Okay, mouth. Okay, put it in a bucket filled with water. What happens? It floats. Okay, just floating on the upper side. Now it floats or sinks? Definitely it floats. Why it floats, the question, right? Now explore the mysterious force that keeps objects like the bottle float. Why? What is some mysterious force is acting upon it? Okay, which is keeping the bottle float. Remember, it is supposed to touch the ground, right? Because earth is attracting, earth has a gravity, right? It's supposed to touch the ground here. Okay, but it's not touching the ground, it's floating on the water. It means some mysterious force is acting on it, which is different than the earth's gravity. What is that mysterious force? Okay, mysterious force, let's understand. Okay, now just push this bottle, you know, just put some pressure here, right? On the bottle, just push it down, right? So you feel an upward push, correct? You clearly see this water is being pushed. You also see that your down push is being opposed by this bottle. Okay, you feel upward push, and try to push it further down, maybe further down, right? Then you will find it difficult to push deeper and deeper. You might push this way, you might push this way, you might push this way. As you're pushing down, you might feel it difficult to push it deeper and deeper, right? This indicates that water exerts force. Okay, this mysterious force I'm talking about. The water exerts force on the bottle in the upward direction. It means you're pushing down, water is pushing this bottle up. Okay, so that's what we experienced it from this activity. The upward force exerted by the water, right? We told you, right? So the upward force exerted by the water goes on increasing as the bottle is pushed deeper till it is completely immersed. Okay, as you push it down and down and down, the force upward push keeps increasing. Pushed, okay, increasing the water. Okay, so the upward force exerted by the water goes on increasing as the bottle is pushed deeper till it is completely immersed. Completely immersed. Okay, now release the bottle. What happens? Okay, now suddenly release the bottle. What happens? What happens if you release the bottle? Okay, it bounces back. Correct? It bounces back to the top. Okay, to the surface. Okay, then what we learned here? So does the force due to gravitational attraction of the earth act on this bottle? See, we are expecting this bottle to be attracted to the ground, right? But we are not seeing this is working. This bottle is being not if looking like this looks like this ball is not getting attracted by the gravitational force, right? What's happening here, right? So why doesn't the bottle say immersed in the water? Okay, we pushed it, but you left the hand, but it came back again. Why it's not stayed back? Is it gravitational force failed to attract it? Let's see. Okay, how can you immerse the bottle in the water? Okay, let's see in the next exercise. Right. So this is an example of water floating. Okay. So now let's just continue the previous topic. Does the force due to the gravitational attraction of the earth act on the bottle? See, it looks like it was not acting upon it. Oh, is it so? Let's understand. If so, why doesn't the bottle, you see, basically it's acting on it. Gravitational force, it's a universal law, right? Universal, the phenomena, right? Earth has a gravity. Gravity attracts the bottle. Even then, the bottle is floating. It means something else is, counteracting this gravitational force, right? What is that? Why doesn't the bottle stay immersed in the water after it's released? Okay, how can you immerse the bottle in water? Okay, let's see that. The earth's gravity pulls the bottle up downwards, correct? It's natural, it's law of nature, right? So it's universal also. Earth's gravity pulls the bottle downwards. Clear? Water pushes the bottle upwards. This is downwards. Water pushes the bottle upwards. We experienced it by our activity, remember. Okay, see this, you see earth's activity and by water's activity, remember. Okay, the weight of the bottle is due to the gravitational force, right? See, it has got weight, it has got some weight, right? Why it's coming? Weight is equal to m into g, and it is good because of weight of the bottle is due to the gravity, m into g, right? It's because of gravity, right? When the bottle is immersed, the water's upward force or buoyancy is greater than the bottle's weight, causing it to rise. Remember, in this case, they fight each other. Okay, one is gravitational force, one is buoyancy or upward thrust, upward force, right? So they're fighting each other, whichever wins. Okay, and either floating or sinking depends on that. In this case, the upward force or buoyancy is winning. Its value is more than gravitational force. That is the reason the bottle is floating. Okay, right. Just now put some pressure and it will go inside, right? What is that? Okay, to keep the bottle submerged, an external downward force is needed. Just put some pressure. Okay, this force should be equal to the difference between buoyant force and the weight of the bottle. See this. So it has got a buoyant force, right? Or the upward thrust for it. You have to counteract that. You have to nullify that, and then only it will keep sit inside. Otherwise, no, it will come back. Okay. What is the summary? All objects experiences buoyant force. All objects experience buoyant when immersed in a fluid. Okay. The magnitude of the buoyant force depends on the fluid's density. What is magnitude? Magnitude depends on the fluid's density. Okay, what is density? You know that, right? Mass per volume. Why objects float or sink when placed on the surface water? Let's do with activities. Learn, understand it. Some activities. Let's take it now. Beaker and fill it with water. Okay. Take a beaker, fill it with water. Take a iron nail. Okay. Take a iron nail and place it on the surface of the water. Put it here. Take a nail, put it here. Don't throw it. Just place it in the surface of the water. Observe what happens. Okay, what happens? It will sink. Correct? It will sink. Observe, the nail sinks. Wow, we learned something. Oh, we know it already anyway, right? So what we learned from it? Okay, the force due to gravitational attraction of the earth on the iron nails pulls downwards. So, right, why this came here? Okay, the force due to gravitational attraction, the earth attracted it. Okay, because what is weight? What is weight is equal to m into g. See, this m is quite more for nail, right? So this gravitational force, or it just it's more than the buoyant force. So it was able to sink. Okay. It sinks because of gravitational force is dominant now. Okay, there is an upthrust of water in the nail, right? Of course, you know that, right? Water has upthrust, which is called buoyancy or buoyant force. Okay, which is pushing upwards. Correct. But who wins? You know that, right? But the downward force acting on the nail is greater than the upthrust of the water, so it sinks. Why? You understood, right? Now, why it sinks? Because this nail experiences both downward pull from the gravitational force and upward thrust because of water's buoyant force, right? Both they fight each other because they are in the opposite direction. Whichever wins decides whether sinking or floating. In this case, because it has got more mass, the weight is more, it sinks, that's all. Okay, in this case, gravitational force wins. Okay, downward force acting on a nail is greater in this case, so it sinks. I think it's very now clear, right? Now let's take one more activity. Okay, take the same beaker but filled with water. Same beaker, okay, filled with water. Now do things. Take piece of cork and as of course iron. Same iron nail take a cork, okay, which is of course lighter, of iron nail as we did previously, right? Do it as we did at the beginning. So place them on the surface of the water. Just place them in the surface of the water. Okay, here. Observe what happens. Now we know it. We can easily guess it, right? What happens? Cork floats. Iron nail sinks. Right. This happens because, see, one is floating, one is sinking. Though they have a same mass. Remember what we are doing it. We took the two things which are having equal mass. Though they have a equal mass, one is floating, one is sinking. Why? Okay, why? Let's see. This happens because of the difference in their densities. Why? Because of the difference in densities, right? The density of a substance is defined as the mass per unit volume. Okay, because see, this has got a higher density, nail, and this has got a lesser density. So what is density? Mass per volume. Okay. Right. So this means that the upthrust of the water, okay, upthrust of the water, okay, on the cork is greater than the weight of the cork. Look at it. This is spread across this, right? Water upthrust is more here. Okay, upthrust of the water is more here, but this is a small, the volume, right? Like small volume, right? The upthrust is smaller, right? So now we have a bigger upthrust. It will, the buoyant force, upthrust force will win. Here buoyant force is very, very small. It is because acting upon smaller area, right? So weight, okay, the cork. So this means that upthrust of a water on the cork is greater than the weight of the cork. So it floats. Very clear, right? What is that? Summary: objects of density less than that of a liquid float. If the density is less than the liquid, if take an object, if its density is less than the density of fluid, it floats. Okay. If the objects of density greater than that of a liquid sink. If the object's density is more than the density of the liquid, say water, it sinks. Okay, it's simple. Right? Now saying density, now it's summary, density decides whether an object sinks or floats. Okay, now let's take some questions. Uh, First question, why is it difficult to hold a school bag, okay, having a strap made up of thin and strong wire? Assume this strap is very thin. Of course, it has to be strong to take the pressure. Assume it is very strong strap of the bag. You can imagine, right? This is the strap. So this is this. Okay, this is wider, right? Imagine it is very thin, okay, to carry this bag, to carry this, the mass, or the weight, or the downward push, pull. Okay, why it is difficult to hold a school bag? That strap is so thin. Why it is difficult? Let's understand that part. So difficulty in holding a school bag with strap made of thin, okay, string is due to the concept of pressure. We learned the pressure, right? What is pressure? Pressure is thrust acting upon an area per unit area, right? Pressure is defined as a force applied per unit area, right? Now let's see that. What is pressure then? Pressure is thrust per unit area, right? Now, okay. Now what's happening? Just imagine. Okay, just imagine two scenarios. I don't have an image for with thinner one. All right. Sorry. Okay, so now imagine this is very thin or very wide, right? What is pressure? Pressure is equal to thrust per unit area, right? Now if it is with wider strap, we have area, bigger area. If the area is bigger for a given thrust, see, thrust is decided by the contents of this bag. Assume you got 10 books and it has got say 10 kgs of things, right? Okay, so this constant in both the scenarios, right? With thin strap and wider strap, right? So with wider strap, what is pressure? Because this thrust got divided by the area and pressure got reduced. Now for a moment, think of it as a very thin strip, okay, but thrust remains same, but area got reduced. Now pressure got increased. Okay, so now the pressure you see here is very high because the thrust is acting on a very small area. Okay, so that is the reason. So when the strap of a school bag is thin, okay, the contact surface area on the shoulder is extremely small, right here. Okay, here contact surface area is extremely small. Okay, this means that force exerted by the weight of the bag, force exerted by the weight of the bag, which is mg, remember, okay, mass of the bag plus acceleration due to gravity of the earth. Okay, which is the contact. Okay, this means that the force exerted by the weight of a bag is distributed over a very small area, right? Okay, this increases the pressure, and this increased pressure can cause discomfort and pain. Okay, here why some kids has to face the pain, feel the pain, right? Not good. So on the other hand, a bag with a broader strap, this is the example of broader strap, has larger contact surface. Now thrust per area, pressure is less. Okay, but see, the weight of the bag is still remains same, but the pressure from this is lesser on the shoulder, which distributes the force over the larger area, resulting in a less pressure on the shoulder. This is why school bags typically have a wider straps. Okay, remember, this is the reason school bags typically get to see wider straps like this. This is an example of it. Okay, making students feel more comfortable to carry their bags. Okay, I think we understood why the stuff, right? Why school bags has wider straps. Okay, because to reduce the pressure, okay, on the shoulder. Why? What do you mean by buoyancy? We learned the buoyancy, right? Let's understand. It's upward thrust. We know it, right? It's a force, upward thrust. Okay, upward force. Buoyancy is the upward force. Okay, what is upward force? Buoyancy is the upward force exerted by a fluid, maybe water, maybe air. Okay, or on any object submerged in it. Okay, we gave an example, we used the example of water being submerged in a water, right? So it's a buoyancy is what? It's an upward force exerted, okay, by fluid, okay, on any object is submerged in it. Okay, you can also take an example of fluid pushing back. See, for example, this is a lemon piece, right? So you just put it inside. See, no, it's not touching the ground. Of course, it's also outside, right? If it is very, very light, maybe it is floating. If it is very, very like a Nile, it would have been here. Somewhere it's in between the measurement, right? Okay, imagine a fluid pushing back against the object. Okay, fluid is pushing it up, right? Remember, buoyant force, right? This force, upward force, gently lifting it up like an invisible hand, right? It's like invisible hand, gently pushing it up. This force depends on what? Weight of the displaced fluid, and is why some things float while others sink. See, remember the flow, the object sinking or floating depends on how much of fluid it will displace. That's also one of the thing. Okay, now let's take a third one. Why does an object float or sink when placed on the surface of the water? Okay, we took an example, we explained this using this diagram, right? Okay, so why does an object float or sink? Okay, you should, couple of reasons, we can explain it a couple of ways. Okay, one way, let's see whether an object floats or sinks. Okay, depends on the battle between the two forces. Remember, it's a fight between the two forces, two opposing forces. They're not acting in the same direction. Remember, two forces. One force is its weight pulling down. Remember, this weight is coming because of gravity, Earth's gravity, right? One of the forces is pulling down, which is weight, right? And the second force is water's upward push, okay, which is called buoyancy. So now two forces are fighting each other. It's a battle between them, and whichever wins decides floats or sinks. Okay, if buoyancy wins, the object floats. Okay, if weight overpowers, the object sinks. Right, next, the other way to answer the same question. All right, so density and shape of the object also play a role. Density and shape of the object play a role. Remember, making flotation a watery dance. Just imagine a watery dance, or your paper boat, just dancing on the water like that, right? Objects of a density less than that of a liquid float. Remember, last just few minutes I explained it, right? If an object has a density lesser than the density of the liquid, the object floats. Okay, if the objects of density greater than that of a liquid, okay, then the object sinks. Remember, and of course the shape of also matters, right? Many times shapes are come up with a way to distribute the thrust and making it effective, and pulling down force lesser, right? This is a couple of ways to answer it. Now let's go for a progress. What is the progress? Let's see that. Okay, so till now we learned thrust and pressure. Out of 6 topics, 5 topics are completed, right? Next topic is Archimedes principle, and let's cover it in some other class.